Hello everyone. In this lesson we're going to take a quick look at matter. We're going to introduce matter and talk about how we can classify it into different types, and of course look at the phases of matter. So first we have the phases of matter. Now you guys know these things. The three common phases on Earth are solids, liquids, and gases. Solids and liquids are obviously matter. They take up space, they have mass, and that's what matter is, anything that takes up space and have mass. We usually get into a little bit of problems because we forget about gases, because we see through them. They don't have a lot of mass, but they do clearly take up space. If they didn't, then we couldn't blow up balloons, we couldn't blow up tires, we wouldn't have sailboats. We have this matter gas that can actually take up space and does in fact have mass. Remember that solids and liquids both have definite volumes. That means you can't compress them. They take up the same amount of space pretty much no matter what. Solids also have a definite shape. Gases, on the other hand, do not have a definite volume. They can expand to fill their container, and you can put them under pressure and compress them. Gases and liquids do share that they take on the shape of their container, although in a gravitational field, the liquid will, of course, have a flat top. It won't expand to fill its container. Outside of a gravitational field, liquid would actually take on a shape of a sphere, but gas does expand to fill its container. Now, a couple things we should remember about matter. Mass is a measure of how much matter is in an object. It's really a measure of inertia. So one way to measure mass is to try to accelerate something and see how much force it takes. The more force it takes to accelerate it, the more matter it contains. So more massive objects resist change more. And it's due to the particles that make up the matter, not due to anything outside of the object, whereas weight is dependent on the object, but also on the strength of the gravitational field that it's in, and that comes from some other object. So weight is from an external force, mass is an internal thing. Weight changes with gravity, mass only changes if the amount of particles change. And then we have the law of conservation of matter, which basically tells us whenever matter undergoes a chemical or physical change, there is no change in the quantity of matter. That means the mass of what I start with and the mass of what I end with will be the same. Now, this is actually not obvious because in a lot of experiments we lose or gain matter to our environment. So when you're trying to keep track of all of this, you do have to keep track of all the products. So when you burn wood, you've got to keep track of the smoke that's produced and the carbon dioxide that's produced and all the little gases that float away, the water that's produced. If you're not containing those, then it looks like we lost matter. But if you do keep track of all those things, then there is no detectable change in matter. Now, we also know that matter is made up of atoms. Atom is from the Greek word atomos, meaning indivisible, and basically the idea here is if you took any sample of matter and started cutting it down into half and half and half and half and half, eventually you would get down to the piece that could not be cut anymore. This idea goes back to the ancient Greeks, but John Dalton did a lot of work with it much later, and a lot of the atomic theory we'll learn about comes from John Dalton, and then we'll see how that's been updated. Now, the thing about atoms is atoms are really, really small. And when I say really, really small, I mean really incredibly tiny. We have to have billions to trillions of them to even detect or measure them. If you had just a spider web and you looked across the diameter of it, you would need about 7,000 atoms to go across the diameter of a single strand of spider web. So atoms are really, really, really small. If you had a glass of water and you blew it up to the size of Earth, then the water molecules, and we'll talk about molecules in a minute, would be the size of golf balls. So these things are almost incomprehensibly little. We need trillions of them in order to measure them, and we'll learn a special way of doing that. Now, like I said, atoms are usually not found as individuals. There's a few things like neon and the noble gases where you get clusters of atoms or gases that just have single individual atoms, but most things are made up of combinations of atoms bonded together. That could be in a crystal like salt, or it could be in a molecule like sugar or water. Either way, that's a couple to several hundred atoms joined together into a single compound or element. Now, I mentioned compounds and elements. Both of those are pure substances. A pure substance cannot be, well, all right. So a pure substance has a constant composition. An element cannot be broken down into simpler things. A compound can be, but doing that changes the type of matter we have. So There's only about 118 known elements. Only about 90 occur naturally. The rest of them are man-made. And a compound is a combination of 2 or more different elements. And there's millions of those. All of the matter that we are aware of is built out of the same 118 elements. But we can make millions of combinations of those elements. So we get different things. So one of the reasons a compound is pure is because it does have a constant composition, but also a compound has different properties than the atoms that make it up. Mixtures, on the other hand, contain a variety of different elements or compounds in them. They are not chemically bonded, and if we were to separate them apart, we would end up with things that are going to have the same properties they had when they were together. So mixtures can be classified as heterogeneous or homogeneous. Heterogeneous meaning different, so they have a composition that varies from point to point. You can see the different pieces in it. Homogeneous mixtures are also called solutions. They're a uniform composition, so every drop of it is like every other drop of it, but that doesn't necessarily mean it is a compound, because the stuff that's mixed in there is not chemically bonded, and you can dilute it or change the concentration of it, so it's not always in the same ratio. So if you have salt water and you stir in a little extra salt, you still have salt water. You changed the concentration of salt, but you did not create anything new. So the different parts aren't bonded, the ratios can change, and separating the solution into its different parts doesn't result in anything new. This chart down here does show us how we can separate matter into different parts. So is it constant or not? If it is, then it's a pure substance. If it can be simplified chemically, it's a compound. If it can't be, it's an element. If it doesn't have constant properties in composition, it's a mixture. If it's uniform, it's homogeneous. And if it's not, it's heterogeneous.